could you write the hydrolysis equation for O2 minus plus H2O? Is good? Yes. 2 OH negative is fine. Same thing, no difference. All right, so you guys are going to show how barium oxide produces hydroxide in solution. Start with the dissociation equation. Is good? I know this is pretty straightforward, but everybody tends to forget this part of the unit because it's like such a small little thing and it's tacked on the end and it's not in a quiz. So I figure by having you write things a few times, it might like go into your head a little bit better. Yes, no, that's a sandwich. Never mind. Thought you had your hand up. And then I'm like, nope, sandwich. Okay, so we can combine these two steps into an overall formula equation. So rather than having to write first the dissociation and then the hydrolysis, you can write an overall formula equation where you simply have the oxide, the metal oxide, plus water gives the metal hydroxide. And as long as you're pretty reasonable, it's easy to balance these. So now that you have two examples there, and you know that the metal oxide plus water gives you the metal hydroxide, I would like you to write the overall formula equation for the following metal oxides with water. What do you think of the reactions I've written? And if you're copying them, there was no point in having blanks there. I could have just typed them out for you. So try not to copy, try and write them on your own. Okay? Are we happy with these reactions? Which one are we unhappy with? Second one. Why? It is not balanced. So I need 2 lithium. So I'm going to put a 2 here. Does that fix everything? Yes. Yes. That would be incorrect. At least I think so. I don't know. And if I don't know, it's probably not important. Okay? Okay. Now, can you guess? Metal oxides are basic. What do you think non-metal oxides are? Metal oxides, basic. Everybody should answer me. Non-metal oxides? Acidic. Thank you. Okay. Non-metal oxides act as acids in aqueous solution. So here are some common non-metal oxides. NO2, N2O5, SO2, SO3, CO2, Cl2O. Now make sure you do not confuse NO2 with nitrite, because those are easily confused. They are not the same. We're not dealing with nitrite. We're dealing with neutral NO2, not NO2 minus. We are dealing with, oops, my arrow went in the wrong place. We are dealing with SO3, neutral, not SO3 2 minus sulfate. So don't think that you have nitrite or sulfite, you have the neutral molecules. And here we go. Here are the formula equations for a couple of these non-metal oxides with water. Let's take a look at this first one. SO2 plus H2O gives H2SO3. Now what I'd like you to do is I would like you on the left-hand side to say, how many S's do I have? 1. How many H's do I have? I have 2. And how many O's do I have? 3. And what if I just took the 2 H's and put them at the beginning, and then I put the 1 S and then the 3 O's? So all I've done is I've taken the atoms and smushed them together into a formula, but not in any order, of course, because it's an acid. The H goes first. And have you ever heard of an ion that's O3S? No, you've heard of SO3. So put them in that order. Okay. So we have made HSO3. What do you know about HSO3? Is it strong or is it weak? Weak. Now, the NO2 reaction is more complicated, but it's not bad. I would like you to think of the 2 nitrogen oxyanions. What's up? Oh, it's so wrong. That's because I cut and pasted. It is not as wrong as it looks, but yes, it's very wrong. So what are our two most common oxy ions of nitrogen? Yes. Sorry.
Why is there each NO? Why did like two acids? Well, when NO2 reacts with water, but why is there only like one? There's one for NO2.
Well, because I haven't balanced it yet.
Okay.
There we go. Thank you for catching that. I hadn't noticed I hadn't balanced it yet. Okay. And I'm going to ask it again, what are the two most common oxy ions of nitrogen? Nitrate and nitrate. What is the formula for nitrate? Is NO3 minus. And if you know nitrate, you also know nitrite, because how do 8 ions relate to 8 ions? One less oxygen. Okay, so your 8 ion has one less oxygen than the 8 ion. The charge remains the same. The only thing that changes is the number of oxygens. So now you know those two. You could make the acids based upon them, HNO2 and HNO3. If you try to make only HNO2 or only HNO3, you will not be able to balance the reaction. Okay, so is it important to know this? Yes, but not like deeply important. Is it important? Yes, because it can show up on your regular exam. Are they probably going to make you write this on the AP exam? Probably not. Okay, I think that the most typical kind of reaction you're going to get will be this one, where you simply take the nonmetal oxide, put it with water, smush them all together. Yes? But if you want to be thorough in learning things, you should know that if you take NO2 and you put it with water, you get HNO2 and HNO3. You get those two acids. If you try making one of those acids, you can't balance it and you'll be like, oh, I'm so frustrated. Oh yeah, I needed to use both of the nitrate acids. Okay? Yes? Because you cannot balance it if there is only one. It won't balance. So this makes two different acids. That's how the reaction occurs. Okay? Yeah. Okay, so what I'd like you to do is I would like you to use the basic smush together principle to predict the products of the following reactions. And when you get to P4O10 hint, if you have to guess at the acid, choose the ic acid. Probably that's correct. Sometimes it won't be, but I'm not going to give you any questions where you'll have to guess. Okay? Yes.
We make like strong acid.
Yeah, this was a strong acid.
Like we can make a strong.
You can make a strong acid, but we're making a strong acid here, and we're making a weak acid here.
But I thought we cannot point an arrow to a strong acid.
But we're making it, right? It will dissociate after this, make it dissociate, and then but we can't reassociate it. We're not making it from the two ions. We're making it from NO2 and H2O. Okay, and truly, if we were writing the net ionic equation for this, we would have 2NO2 plus H2O gives 2H plus NO2 minus plus NO3 minus. So they would be dissociated. Did that make sense? Yeah? Okay, cool.
Oh, okay. I haven't even done 13. Let's try.
Which one? The last one? As long as it's the last one, I don't think they're ever going to give you one like the last one, but I do want to show you. Yeah, yeah. You need an acid that you are familiar with. Okay? You should get a reasonable acid that is on your acid chart. So if you have to guess the acid, choose the ic acid, and the ic acid would be phosphoric. I'm never going to make you guess the acid. I'm just going to have ones where you smush it together and it makes it, it'll be like CO2 or SO3 or SO2, ones where it's obvious. Smush them together, make the thing. But I did want you to see that other reactions do occur and they will balance and everything can be okay. All right? Now, once these acids are formed, of course, they can ionize. The strong ones will ionize 100%, the weak ones less than 100% to form H3O+. Could you please show those reactions? Is good? Okay. Metalloid oxides, oxides beside the staircase. Now, to be fair, when I looked up lists of these things called amphoteric oxides, I found lists of a whole bunch of things that were not near the staircase. They were not metalloids. And I'm like, okay, but chemistry 12 tells us that metalloid oxides are the ones that are amphoteric. So we're going to go with that for right now, okay? Because it's kind of true. It's kind of true, right? And we'll talk a little bit more. There are also metals that will be, there are some metal hydroxides. Okay, these ones are going to be not group 1, group 2. Group 1 and group 2 are acidic. Those are the ones we already talked about. NaO, Na2O, CaO, BaO, Li2O. Those ones are acidic. Now, amphoteric. It's almost like, it sounds a little bit like what? Amphiprotic, but it has a slightly different meaning, okay? So in water, an amphiprotic substance will both produce H+ ions and OH- ions. The reason we need the word amphoteric is because these substances do not produce H ions in water and they do not produce OH minus ions in water. And the reason they don't do that is because they have a very low solubility. And that's why they cannot just, if you dump them into water, they will sit there and they will not make the solution acidic and they will not make the solution basic. Does that make sense? That's why they're not amphiprotic. Because if they were amphiprotic, if I dumped them in, they would make some hydrogen, they would make some hydroxide. We would compare their Ka with their Kb, and we would determine which one prevailed. But because they are low solubility, there is no OH minus or H plus produced. Sorry, H3O plus, I should say. In water. And that's why it's not amphiprotic. So very little to no hydrolysis occurs. Therefore, they do not just act as acids or bases in water, in plain water. But the reason they are amphoteric is because if you put them with an acid, they will react with the acid. If you put them with a base, they will act as a base. It's very similar to, you remember when we had a low solubility compound, just a hydroxide? Yeah, say we had low solubility, MgOH2. Yes, you remember that? And we could react it with HCl, and this is a solid, and this is aqueous, and hydrogen will rip the hydroxides off of that, okay, and it will then cause it to become water and then release the magnesium into solution. So you would end up with Mg2 plus 2Cl minus plus 2H2O. So do you see how that magnesium hydroxide is on its own not going to be very basic because it is low solubility? But it can react with an acid, and I can in fact get it all to react with an acid, okay, because the acid will drag it to completion. That is what is happening here. So here is an example of zinc oxide, which you'll notice zinc is not a metalloid. It's one of those other metals I was talking about. You do not need to memorize who will be the amphoteric oxides, okay? You'll probably be told something like zinc oxide is an amphoteric oxide, right? You'll be given that information, and then from that you have to say, oh, what is amphoteric? That's when it can react with an acid and it can react with a base, okay? You might maybe know this one because it's actually fairly straightforward, yes? If we have our zinc oxide, our amphoteric oxide, it can react with an acid and we have a simple double replacement reaction, yes? Could I expect you to be able to predict those products? Yes. Now let's take a look at the next one, where this amphoteric oxide acts as an acid. Now it's reacting with a base, and what do we get? We get a salt, Na2ZNO2, and water. Do you like the font I found? Okay, so this is funky. We don't know what the heck is happening here. It is a crazy thing. Would I expect you to predict that?
No.
No, okay? Don't worry about it. Just know that the amphoteric oxide can react with the base. You don't have to predict the products. So here's an example, okay? We have Al2O3. Once again, is that a metalloid? No, it's not. I don't know. All the examples I could find were with like zinc and aluminum. They weren't with metalloids, but these are sort of a list of things that can be form amphoteric oxides. The ones that I would expect you to predict to be amphoteric would be arsenic, because it is a metalloid. Gallium and germanium, because it is a metalloid. And there's not even zinc in this list, and zinc is one of them. Like I don't know. You know what I mean? Like, nah. I think honestly, the option of anybody asking you about an amphoteric oxide, me, AP, is really low. I don't think you need to worry about it too much at all. So don't be like, I'm so confused. How am I going to remember it? You don't need to. It's okay. If you know what the word amphoteric means, you probably are good to go. Okay? So here we have a question, and guess what it says? It says Al2O3 is an oxide that can react with acids as well as bases, and we are given the two equations. And then you are asked which of the following describes that oxide. Could you please see if you could answer that question?
Oh, wait.
How many people feel they're done? One. Okay. Keep working on it. Keep talking about it. Don't give up.
It's like semi. Yeah. Are you nice? I think I'm leaving them. It's more like, I don't think it's E.
I'm locking it.
Yeah, it's like what the heck is this?
What do you guys think?
It's not a non. Yeah. Oh, that's possible.
You're so artsy and boys.
It's either
Probably.
like it can be with cold.
You think it's Z? I think you're right. It must be Z.
Yeah, but acid. has to be
Okay, are there any things that we can eliminate here based on incorrect information in the answer? We can eliminate, it is a peroxide, because peroxide, if you don't remember, is the ion O2 minus. Okay, a peroxide. And peroxide can be in the form of H2O2, Na2O2, Ca O2. So if you ever see like an oxygen containing ionic compound or water that doesn't look right because it's got the wrong number of oxygens, or it's got the wrong number of sodiums or whatever, you know you've probably got a peroxide, okay? Because the charge is different. In fact, what would the charge of each oxygen atom be here? Yeah. Each O is -1. And we are going to be learning either later today or next class about oxidation numbers. In peroxide, the oxidation number of oxygen is -1. Bridging units here. Is there anything else we can eliminate from our answers because it is obviously wrong? Why is D wrong? Because aluminum is a metal. Therefore, what can we do? We can eliminate our non-metal answers. So now we're left with an amphoteric metal oxide or a neutral metal oxide. And what does it mean to be amphoteric? It can react with acids as well as bases. So therefore, our answer is A. Yes? No. Neutral oxides are different. They are things that actually do dissolve in water and do not react. So water is a neutral oxide. You can't make a solution of aluminum oxide. It does not dissolve. Okay? All right. If you want to see a video about that question, it's here, but we've basically just gone through the process. Okay, another word for oxide compounds that react as acids or bases is anhydrides. You need to know the word anhydride. Anhydride means without water, which means that you can add water to it and it will react. Anhydrides react with water to produce acidic or basic solutions. So an acidic anhydride, we're not learning anything new here. We've just given it a new name. Okay, so if you're like, hang on, I feel like we just did this 5 minutes ago, the answer is yes. Yes, we did just do this 5 minutes ago. An acidic anhydride is a what kind of oxide? They're oxides of elements on which side of the periodic table? They are on the right side of the periodic table. Acidic anhydrides are what type of oxides? Non-metal oxides. And really the only reason we're filling this in is so you can hear the word anhydride numerous times so it becomes more of a word and less of just a weird thing, okay? Some examples of acidic anhydrides are SO2, SO3, Cl2O. I'm sure you could name a few more at this point. The reactions, please write the results of those reactions. Whew. Scary.
My Sprite is delicious.
My Sprite is delicious. Yes.
Wait, no. Oh! What? Why is not you?
Is good? Yes? Hypochlorite. And if you've forgotten about how the hypo and the per work into your series of oxygen ions, there is ClO4, ClO3, ClO2, ClO. They're all negative, 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 negative. Could you name those 4 ions? I'll give you a start. This one here is chlorate. If you know that's chlorate, you should be able to name at least the one below it.
Chloride and ClO2.
What is ClO2?
Chloride.
Chlorite. And what do we have to add on to chlorite to make it one less oxygen? It's still going to be chlorite, but we're going to add on hypo. Hypo means below. A hypodermic needle goes below the skin, below the dermis. Yes?
Yeah. Like, what are you gonna do?
Now, above chlorate, we have still chlorate, but we have to add something to it. What do we add to it? Per. That's from the same root as super, which means above or more. So oxide is O2 minus. Peroxide means you got more O's. Yes? O2 2 minus. At any rate, there we go. And a basic anhydride. Basic anhydrides are oxides of the elements on which side of the periodic table? On the left. Acidic anhydrides are what type of oxides? Oh, this should say basic. Basic. Sorry, I need to fix that. Basic anhydrides are what type of oxides? Metal. Some examples, Na2O, CaO, MgO, Li2O, etc. Write the reactions with water. Are we good with that? Excellent. Are we ready to move on to acid rain? Okay, acid rain is just an application of this stuff. Okay, so is normal rain. Oh, and there's some AP stuff here, just showing the reaction of the metal oxides producing a salt and water. I don't know if you really need to know this. See, I don't think you need to write these equations on the AP exam. Even if you have to do so, it would only be for 1 mark and not worth the memory effort. I wouldn't bother memorizing anything beyond metal oxides are basic, non-metal oxides are acid, metallite oxides are amphoteric, and you should be able to write the reactions of metal oxides with water and non-metal oxides with water. Okay, summary, bam, there. We can come back to those later. I really don't think they're that important. So let's move on. Oh, And just so you know how unimportant it is to know the amphoteric ones, they can't even decide consistently between different charts I looked up which ones are amphoteric. According to this table, these are the amphoteric ones. Okay, and then according to this one, these are your amphoteric ones. Where did zirconium come from? And I know that iron, I think, is another one, but you know, like that's all I have to say about that. Okay, like notice the inconsistency. Therefore, it's not important to memorize the details. Just know the big broad strokes. And then finally, here's some examples of basic oxides, amphoteric oxides, acidic oxides, and then finally, you remember we talked about neutral oxides? These do not react with water. But you don't need to know anything about them or memorize them or anything, okay? I don't think they'll come up at all. Yes? Nobody's going to ask about them. I'm not, AP's not. They're just there because they exist, okay? Normal rain and acid rain. I think that you guys could write this first equation. This is page 117. Since our atmosphere naturally contains CO2, which is an acidic anhydride, because it is a non-metal oxide, some of this reacts with water, the rain, to make the rain slightly acidic. Could you please write the product of the reaction of CO2 plus H2O? Yes. I think that's a mistake. Fix. What do you have, once you have H2CO3, what can you produce? H plus plus HCO3 minus. What would we have here? Any biologists recognize that?
Oh, carbonic acid buffer.
Carbonic acid buffer. This is our blood buffer. Right? Because what do your cells do? They make carbon dioxide. What does the carbon dioxide do? It absorbs into the bloodstream. And when it dissolves into the bloodstream, it makes carbonic acid, which then dissociates to make H plus and HCO3 minus. And then we get a buffer, maintaining your blood at a fairly neutral pH. Okay? So natural rainwater actually ends up with a pH as low as 5.6. So if you're like acid rain, pH 6, pH 6 is not acid rain. pH 6 is just natural rainwater, normal rainwater. Why do we have this low pH? It is due to what in the air? CO2, okay? You'll notice there's a lot of repetition here. Okay. Acid rain, on the other hand, and this reaction, this is also responsible for acidification of the oceans. You know, with global warming, we got more CO2 than before. So this is also responsible for acidification of oceans and lakes and stuff. If rain has a pH lower than 5.6, It is called acid rain. And acid rain is also caused by acidic anhydrides, but not CO2, because CO2 is just natural, or at least mostly. What are acidic anhydrides? What's another word we could use for that? Non-metal oxides. Acid rain is mostly caused by humans. Humans. And what do we do that causes this? We burn fuels. For example, coal. Coal often contains sulfur impurities. And when you burn the sulfur reacts with oxygen and you get SO2. In your car, if you have an internal combustion engine and not an electric vehicle, we get oxides of nitrogen. So how do these work? When burning coal or other fuels, you get S plus O2 gives SO2. Easy? Was that easy?
Yeah.
Yes. Now, would you be able to write a reaction for SO2 reacting with water?
Yeah.
I hope so. We just did a whole bunch of them. This thing is an acidic what? SO2 is an acidic what? Anhydride. See, we're practicing writing the word, so it seems less foreign. Now, you can actually get further oxidation. Oxidation, what is oxidation? It is stuffing oxygen onto things. But what else is it? It is also losing electrons. Leo, the lion says, grr. Losing electrons is oxidation. What does the G stand for? Gaining electrons is reduction. So what are we doing with our sulfur? We are further oxidizing it, okay? And in fact, what I could do right now is I could give you a quick little preview of what we're going to learn tomorrow, and that is oxidation numbers. They're kind of like charges, but not really. They're made up. Do atoms in covalent compounds have charges? No. But we assign them oxidation numbers that are charges, okay? So if you had to guess what the oxidation number of sulfur is here, without knowing anything about it, you're going to base it on the fact that you have two oxygens attached to it. And you're going to base it on the normal charge of an oxide ion. We have 2 times oxygen which is 2 times the normal charge of oxygen is -2, so that is equal to -4. So the oxidation number of sulfur is +4. What is the oxidation number of sulfur over here? The oxidation number is, we got -6, right, with the oxygens. So this is going to be +6. And look, the oxidation number got bigger. That substance was oxidized. When the oxidation number gets bigger, the substance is oxidized. When the oxidation number gets smaller, when the oxidation number is reduced, we have reduction. Little preview of tomorrow's lesson. Okay, did you guys follow that? When the oxidation number gets bigger, oxidation. When the oxidation number is reduced, gets smaller, that's reduction. Okay. Yeah.
We weren't explaining that by
Yeah. Yeah. That's why we do chemistry as well as bio. Because they don't. Yeah, you're reducing the charge. Essentially, you're reducing the oxidation number. All right. While we're here, could you guys please balance that reaction?
Yes.
Is that what you guys got for balancing? And if you're like, how did you do that? I said, I have an odd number of oxygens on the right. I can only have an even number of oxygens on the left. So I doubled this, and then everything else just became easy. Is good? Okay. Now let's say we have some SO2. It can react with O2, and it can form H2SO3. Let's find the oxidation number of sulfur here. Buzz. Okay. What is the normal charge of hydrogen? +1. And, or -1, but only in hydrides. And is this a hydride? No. Hydrides are where it's like it has a negative charge. Do hydrogens in acids have negative charges?
No.
No. Therefore, what's the charge of hydrogen? +1. We have 2 hydrogens. Therefore, that's 2 times +1, which is +2. Right? So we have +2. Now from our oxygen, we have 3 oxygen. What's the normal charge of oxygen? 2-, right? And so how much is that? -6. What do these make together? -6 plus +2 is equal to -4. So what is the oxidation number of sulfur there? +4. Oxidation number of sulfur here. What's the oxidation number of sulfur in SO2? +4. Have we had a change in oxidation number? Sulfur was +4, now it's +4. Was there a change? Is this a redox reaction? No. Okay, so if the oxidation number stays the same from side to side, there is no redox reaction. All right. So we get sulfurous acid and we get sulfuric acid. Sulfur here, plus 6. Sulfur here. Yeah, yeah. What's the oxidation number of sulfur in H2SO4? What would you predict? 6. It is 6 because we've got -8 here and we got +2 here. And so that's going to be -6. Don't worry if this is going past you way quickly and you're like, what just happened? We're going to actually learn a proper, structured, nice, tidy way of doing this next day. Okay, this is just a preview. Okay, so if you're like, preview, scary preview, don't preview. Don't worry, next day it'll all make sense. Okay, I got 2 people packing up. Why is everybody else packing up? I know you have art club. You are allowed to pack up and Rigel is allowed to pack up. I don't know why everybody else is packing up. Yes. You may go to your doctor's appointment. Okay? And everyone else is like, oh, I think my grandmother may have died.
Yeah.
Oh my gosh, there was a student one year when I was at Alpha, their grandmother died like, I don't know, 4 or 5 times so that they could miss tests. Uh-huh. I'm like, really? We couldn't have come up with like a different, relative at the very least? Anywho. Nitrogen, when it reacts with oxygen, you can get one of 2 things. You can either get NO or you can get NO2. So we have nitrogen plus oxygen gives either NO or it gives NO2. Now, NO is pretty much unreactive in water. It was one of those neutral things. So it actually undergoes further oxidation. So we get our NO, then reacting with more O2 to eventually give us NO2. So in cars, what's the primary thing we're making? NO2. What's the primary thing we're making from burning coal with sulfur in it? SO2. Yes? So NO2, SO2. What happened back here? Oh, and you can also get SO3. Okay? You will have to go back and read this because I know that nothing is going into your head right now. Okay, so you're going to go back, you're going to read this, you're going to read the Hebden section associated with it, because this can be on your test, and I know that it's not going in right now. But look, most of it's just to do with the the acidic oxides. Look, we have NO2 again, reacting with water. What do we get? HNO2 and HNO3. Is that anything different than before? No. Natural sources. Volcanoes. You can actually end up with nasty acid rain from volcanoes if you've got a big explosion. I was like, oh, you just look so like peaceful. And then lightning can produce HNO2, which can form HNO2 and HNO3. Natural production from acid rain. Guess what? There are carbonates all over in nature. They contain guess what? The carbonate ion. So for example, CaCO3 is both limestone and marble. We're not going to finish this. So I'm just going to tell you that you should read this stuff and then you should do some of the anhydrides and acid rain worksheet. Okay? Do some of this. Whatever you have time for tonight. Yes?
So what would be on the Friday?
Friday quiz is titrations and buffers.
Oh, okay.
Okay? Not the anhydrides and acid rain.
It's the other concentration stuff will be on the quiz. Could you close like one section? It's gonna go.
Yeah, but like you
Okay.